All right, in this problem, we have a relation defined on the set of integers as x is related to y if and only if x squared plus y squared is even. And they ask us to prove that R is an equivalence relation. In other words, they want us to show that R is reflexive, symmetric, and transitive. Reflexivity should not be too hard because if you square x and square x again and add them, it gives you twice of x squared, which should be even. Symmetric should be easy. If x squared plus y squared is even, then y squared plus x squared is even. Now transitivity is the one that will probably take us a little bit more time to do. That's not too hard either. So let's go ahead and do this, okay? Okay, R is reflexive. To show that, let's let x be an integer. Then what's x squared plus x squared? Right here. Then x squared plus x squared, which happens to be 2x squared, is an even integer since x squared is an integer. It's twice of an integer, so it's an even integer. Hence, x is related to x. This is true for all x's because x was an arbitrary element of integers. The second thing we need to prove is R is symmetric. Suppose now x and y are integers and they are related. X is related to y. Suppose x is related to y. What does that mean? Then x squared plus y squared must be even. But y squared plus x squared is the same thing as x squared plus y squared. So y squared plus x squared is even. Therefore, y must be related to x also. Hence, R is symmetric. We assumed x was related to y, and y is related to x also. Third one is to show that R is transitive. For this, we suppose that x is related to y and that y is related to z. And we want to show that x is related to z. Okay? So what does x related to y mean? X is related to y means x squared plus y squared is even. So that means it's twice of a for some integer a. What's y related to z mean? That means y squared plus z squared is twice of b for some integer b. So, what does this mean? Well, let's add these, okay? If we add all of these, we get x squared plus 2y squared plus z squared. On the right side, if we add those two, we get 2a plus 2b. Now I'm going to move the 2y squared over to the other side to get x squared plus z squared is 2a plus 2b minus 2y squared, which we know, we see it as even. So let me write that down. So x squared plus z squared is 2 times a plus b plus minus y squared, which we can call it as 2k, where k is a plus b minus y squared, which is an integer. Hence, x squared plus z squared is even. This means that therefore x is related to z, which means that r is transitive. So now we've proven that R is an equivalence relation. To find the equivalence classes of that equivalence relation, x is related to y if and only if x squared plus y squared is even, we'll start with the equivalence class containing 0. Okay, so the equivalence class containing 0 is the set of all y's integers such that 0 is related to y. But 0 is related to y is the same thing as 0 squared plus y squared is even. Well, what's 0 squared plus y squared? This is the same thing as y squared is even. Or when y squared is even, then y is even. Or when y is even, then y squared is even. So this means that y is even. This means that the equivalence class containing 0 are the set of all even integers. Okay? If I have any even number, then it's related to 0. Conversely, if a number is related to 0, it must be even. All right. Now let's see a missing value here, an integer 1. Let's calculate the equivalence class containing 1. This is a set of all y's. 1 is related to y. And again, 1 is related to y means that 1 squared plus 1 squared is even, which means that 1 plus y squared is even, which means that y squared is odd. Because you add 1 to it, it became even. But y squared is odd is equivalent to saying that y is odd. So when y is odd, it's related to 1, or when y is related to 1, then it must be odd. So the equivalence class containing 1 is the set of all odd integers. So these are the two equivalence classes of the relation, this and this one. We have two equivalence classes.